Yeah, everything else can just go there. Oh. Did we all finish the quiz and everything? All right, excellent. So thank you so much for being flexible with me. I don't typically like to do things in a different order. I usually like starting with lecture, but I had a meeting that ran a little long, so thank you again for being flexible with me. All right, so like I said, we're going to start looking at our electronic structure as well. But we'll probably start off with some balloon exploding. But actually, before we even get to that, I wanted to talk about something else. So did y'all, it's like going around on the internet, you know, I just saw it on Instagram, that's why I was thinking about it. But it's going around on like Instagram or TikTok, whatever, that like, oh, there's ammonia in the Starbucks pumpkin spice. Have you guys heard of that? And then the explanation that I read on the article real quick was like, ammonia is used to color it. I was like, what? Ammonia is colorless. So then I had to look into it more. And okay, so this is, the whole point of this is chemical literacy for y'all. And so actually it's referring to this chemical. So this is what actually gives it the caramel color, so not ammonia. So that was why I was so confused. And so this compound, all we really need to take away is this is formed when you brown foods through the Maillard reaction. And so my new hobby this summer is making smash burgers. I've been trying to perfect my smash burger technique. And so yes, that's invoking that Maillard reaction, right? So you want to get it nice and crispy. And then this is where the ammonia comes into play though. So people started flipping out because the kind of known synthesis does involve ammonia. So yes, you know, maybe there would be trace amounts of ammonia in the final product, but right, you wouldn't really expect ammonia to be in the final product. So kind of this goes back to just how they make organic compounds or really anything, because right, I read these articles and the way they talk about chemistry is so scary. They're like, oh my gosh, the chemical was made with things that were like petroleum. I was like, well, yeah, because it's an organic compound, so that's how you make stuff with organic reactions. And so, right, don't listen to the media when they try to scare you with stuff, but then, right, delve into the article and, well, what were they actually trying to tell you? So this is why scientific literacy is so important, since, right, obviously an article can't even report what the correct caramel coloring is. And so if you look in this Wikipedia article, this is used in like Coke and a lot of other things, like Coca-Cola, not cocaine, to give that caramel color. But yeah, I probably personally wouldn't be worried about this. in your pumpkin spice latte, but anyways, more debates for another day. All right, so now let's start looking into, and again, right, we want to build up our chemical literacy. We also want to learn about our reactivity. And so we're going to start off with hydrogen. And so let's, of course, look at hydrogen. And so now we're taking what I call our second tour of the periodic table. So now we're going to go kind of hopefully slower, and this is where definitely ask me questions, because we're kind of going to be talking about a lot of concepts to just explain our reactivity. And so we're looking at hydrogen here. And so, of course, right, we said it was a diatomic. So that was a quiz answer. So, and I highlighted the other 6 diatomics over here. So again, good information. And so we'll kind of be getting into the, well, why is it a diatomic? And so now let's look at our electronic structure. And so let's start off. So again, we're starting with hydrogen. And so you could maybe highlight this or mark this, or you may want to wait till later. And so this is called our S block. Well, what the heck does that mean? And well, let's maybe back up a tad. So, right, when you were in school, did you have this kind of Bohr model of the electron? So, right, we have our Bohr model, you have kind of your first one, and they always like do this pattern, right? We have 2, we have 8, right, 18, 36, right, something like that. And so now we really want to dissect this and truly get a better understanding, right? And so that's something to first appreciate, is this kind of Bohr model is a very oversimplified model, right? And it's just kind of our onion model in saying that things kind of come out in these layers. But what we're going to learn now, and again, this is where we're taking a slightly deeper understanding now, is what we have computational chemistry, which, by the way, did you see computational chemistry won for the Nobel Prize? I'm not personally a big fan. I'm a hands-on chemist, but, you know, whatever. It's okay. We'll live with it and move on. So anyway, computational chemistry is important. And so now we can actually figure out the electron density. So that's what is being calculated with these modeling softwares. And again, it relates back to quantum mechanics. But what we just need to appreciate is, okay, here's our pretty picture of the orbital. This is what it looks like. And so this is how it starts. And so the s orbitals are all spheres. So nice big sphere here. And so right, that's where it starts with hydrogen. And so you might want to write this, because we're going to learn our electron configuration. And so we start with our 1s here. And so this would be our S1. So all these have one valence electron, right? We'll come back to this idea. So now it's starting to tell us more about the reactivity. And then this is where this P table, so again, ptable.com, this is going to be really helpful for this part. So if we go over and click on the big electrons up top, it kind of arranges it a little differently. So now it put helium over here in the s block, just to emphasize that it only has our s orbital filled, and well, we'll save our thought for helium in a second there. And so let's look at hydrogen. So if we hover over hydrogen, it tells us over on the left-hand side the electron configuration. So that's there, the configurate. And I need more like pointers and hands. Right, so we have configuration here. This is just rewriting your electron configuration expanded. And then we don't need to worry about the other information. So right, we're just on our hydrogen. And so now we can start to fill in our electron configuration. And so again, our electron configuration is basically just our shorthand way of telling us where our electron is. So for hydrogen, and again, right, well, you fill it up in order, so we're going to be going through this. And so its electron is in the first level, so this is our 1 here. It's in the S block, and then there's 1 electron there. So again, right, this is our main kind of energy level. And then, right, writing out where the electrons are. And so now, let's write, and again, this is, I think, chapter 3, but it's helpful if you start kind of putting these ideas together. And so the Lewis dot structure, what it attempts to do is say this in a visual way. And so if it has 1 electron, then we can just write that, boom, a little h like that. And so this is starting to tell us the picture of why hydrogen is a diatomic then. So right, you can look at it and, you don't really have to know too much about chemistry to kind of notice, well, that does look a little weird, just like a little dot there. So it isn't stable like that. So in its elemental form, right, 2 of them come together. So now I'm just kind of emphasizing how 1 electron from each hydrogen comes together, and we make that single bond there. So again, right, this electron configuration information is all very useful. All right, so let's explode some hydrogen and see its flammability properties in action. So of course, hydrogen is a gas. Yeah, and then probably you 3 in the front row, if you just want to, like scoot back, maybe sit a little back, just in case, just to be safe. I think, Catherine, you'll be okay, since you're kind of on the end, but just like, the 3 in the middle. And then who wants to be my volunteer? Sarah? All right, so yeah, if you could just hold out this stick like this. All right, from you. And so let me, yeah, right there is perfect. And then actually let's dim the lights a little because we want to try to see the difference. If I can during the lights. Sorry, obviously don't know how to use my lights. I'm trying to make it darker. How do I make it darker? I was trying to figure out how to move this stupid. All right, I don't know how to use those. All right, let's, whoop. So we're just going to light it. If you're sensitive to loud noises. That was good. Everybody awake? So that was hydrogen, right? You saw. All right, so that was hydrogen, right? So nice big flame. And so now let's try that. And we might as well just keep going. Do you want to continue to be my volunteer victim? Sure. And so while you're standing there for a second, let's just write out. So now we'll revisit oxygen. But I just want to write out, so here's its electron configuration. I'll go over this more slowly why this is. And then again, oxygen we said was a diatomic. And so now let's watch this combustion. All right, yeah, hold it out again. Thank you for your bravery. And so pay attention again. So now this is just oxygen. See if you can compare how big the flame is. not as dramatic. So, right, kind of note that how much more explosive the hydrogen was. You can think about that too. What was it called? The Lindenberg, right? When they used to do the blimps with hydrogen instead of helium. It's a bad idea. And so now we're going to do the combo balloon. And so kind of the key, and so really we're doing the same reaction, right? H2O plus oxygen in some form, right, leads to this combustion, obviously, of water. But what happens when we kind of pre-combine them, and so they might be a little bit more explosive in that reaction. So let's kind of compare. I'm trying not to come on, stay lit candle, anticipation of the worst. So that was really big, right? And so that is right with the extra, they're like combining in the balloon, really reacting explosively. Give a big hand for Sarah. Yeah, that was scary. We probably scared some other classrooms. All right, so that was excellent. And casual chemistry class. Just another day of exploding stuff. And so, right, that's just another good reminder of, again, we had our elements. We watched them kind of combust differently, and then, again, combusting really together to make that really explosive compound. Yeah?
Sorry, were you going to kind of touch more on the types of orbitals?
Oh, yeah. So we're going back to that.
Okay, cool.
So sorry, I just wanted to get the fun explosions out of the way. And so now we'll go back to orbitals, which I know is oh so enthralling. Actually, it gets me excited, but that's just me. All right, so continuing our tour of our periodic table, which is less exciting than blowing things up. And so I thought about bringing helium, but I didn't. So helium, right, is not that exciting to combust, since it's really just the air kind of popping out, once that balloon bursts because of the, obviously, the heat. Well, why is helium unreactive, though? So now we can answer that with our periodic table. So now we've gone over and we've filled up our s orbital. And so the other thing to note, so there's a couple of helpful things that keep us in check. So the s orbital, it can only hold 2 electrons total. And so if we go back over to our notes here, maybe you want to write this about the orbital, right? So the s, so holds 2 electrons max. And so now going with our electron configuration, so now we'll look at helium. And so still first energy level, which also corresponds to, right, the first row. So that's kind of helpful. And then again, we are in our s orbital, and now we have 2 electrons. And again, right, that matches up. So right now we're also just looking at neutral atoms. So of course, right, helium is atomic number of 2. So that means it should have the same number of electrons, since, again, we're only focused on the neutral right now. All right, so then let's continue our tour. So then we're going in order. So 1, 2, 3 brings us back to lithium, right? But now we're on our second row. So now we've started our second shell. So again, if you want to correlate this back to your Bohr model from back in the day, this is where we are. So now we've started, so we have our s orbital. So this would be n equals 1. This is now n equals 2, where we have our 2s in here as well. And so let's at least kind of appreciate it. This is where, again, these visuals are nice I can pull it up. And so it's down at the bottom. So if you can see the little circle here, and it might be better to look on your own personal device. I don't know why the colors and contrast aren't amazing. But what you're trying to tell, and let's look at hydrogen. So right, hydrogen is just that single sphere. And then imagine, so all of these orbitals, they have a node, which just means that there's an area where there's nothing in between. So think of it, we have our ball, we have a small node where there's no electrons. Then the next onion layer starts, so our next sphere of our 2s. So again, right, you can see that. So our hydrogen 1 ball, and then go down to lithium, and you can still see in the very center, right, that 1s. And so now we can write our electron configuration. And so we just want to start at the beginning again. So lithium, so you start from the top. So 1s2, right? So we have to completely fill in that first s orbital. And then now we can go to 2s. Then it's 1, because again, right, lithium is our element number 3 here. Atomic 3 has to have 3 electrons for our neutral. And then remember, we can add our superscripts, so 2 plus 1, that gives us 3 for our 3 electrons. Other ways to abbreviate it, and so we have what's called the noble gas abbreviation. So basically, you go to the previous noble gas and start there. Right now, we're pretty early on that it doesn't save us a lot of ink, but I'll at least demonstrate what that would look like. So we could say or, and then we have helium in these brackets to signify electron configuration of this element, and then we can continue on from helium. So then we have helium and then 2s1. So same meaning, and I believe the P table should reflect that, so let's double check that. So yes, so right, you can see that. So under the configuration, so it has the abbreviated with the helium 2s1, or what they call expanded, where it's fully written out for you. And so again, we're noticing our trend. So our first row here, right, that's why they're the alkali metals. That's why they're water reactive. We can also get into, that's why they're always in the 1+ oxidation state, right? Because they're always going to be losing that 1 valence electron. And so that pattern is going to be repeated, right, with this NS1 pattern. So sodium, right, is going to be 3s1 for its valence electron. Potassium 4s1. So again, just showing you why they all have similar reactivities. And so let's keep going. So then we have beryllium. So again, we'll just kind of be explicit for now, so we'll fill it up. So now beryllium's electron configuration, 1s2, 2s2, or again, our abbreviated form. For the electron configuration of beryllium, we again want it to reflect this. And so what I mean by this is, so sometimes, again, this is like in high school, you have this oversimplification where it's like, well, just give, one side a dot or something. And so the problem with that, and you even see like books like this where it has, magnesium, I've seen this, and I just don't agree with this because it doesn't reflect our electron configuration, right? So we want to show we need to fill this s orbital up first. So more appropriately, we want to keep the 2 dots on one side. So it doesn't matter, what side they're on, just as long as they're together. And again, we'll kind of show the why and what we're trying to translate out as we continue. And so now let's start the P block. So now boron begins our P. And so let's look at, well, what is our p block. What are our p orbitals? And so now we have our p orbitals. So there are 3 p orbitals, so px, py, and pz. And there are these dumbbell shapes, and they have one node. So here, that's where its node is considered to be. So again, that's just an area of no electron density. And then they're named for their axes. So of course, px lies on the x-axis, py is on the y, pz on the z-axis. And then each one of these orbitals can hold 2 electrons. And so that means, right, there's 6 electrons total then in our p orbitals. So these are subshells. So each subshell holds 2 electrons. There's 3 of them. And then if we go back to our Bohr model to kind of compare, so now in this n equals 2 level, we have s orbitals that are possible, and then also our 2p. And so, right, you can see, oh, that's where we get back to 8. So 2 from the s, and then 6 from p. So 2 plus 6 gives us 8. So now it's all starting to make more sense. Other helpful hints, well, if the p block can hold 6 electrons, it's going to be 6 across. So 1, 2, 3, 4, 5, 6. So that helps you remember as well. And so let's just continue on with boron. So if we click on boron, I have to try to scroll down. And so there is its orbital shown. So again, it's kind of a funky picture, but just trying to show the dumbbell there. There's our representation. And it doesn't really matter which p orbital it's in. We don't know. It kind of looks like they stuck it in px, but it doesn't matter. You just have to represent a p orbital. And then we can write our electron configuration for boron. So boron, so now we're at 1s2, 2s2, then we're still at the second energy level, and now we're 2p1. And then we can add up our electrons again, so 2 plus 1, so that's 5. That matches right for neutral boron. Then I'll rewrite it in the abbreviated form, just so we can see. And then, right, so now we can emphasize, so these are our valence electrons. So these are just the outermost electrons that are available to, again, do action. So we're kind of, again, seeing this theme repeated. So now we can say, right, boron has 3 valence electrons. We can also note that from our periodic table. So it has 13 here, but, right, just take away that 1, group 3, because basically we're ignoring all these. And then, right, 3 valence electrons. Or your periodic table. So other periodic tables, right, they have this 3A, 4A, 5A. So that can help you understand the number of valence electrons, right? So it corresponds. So 3 valence electrons, 4, 5, 6, 7. So all coming together. And so again, with boron, if we want to write the Lewis dot structure, I want to, again, reflect this. So I'm going to put 2 electrons on one side together, and then 1 by itself. So boron, so 1, 2, 3 is fine. You know, it doesn't matter what side you do it, something like that. And so this would be acceptable. What I'm going to say is okay is if you also distribute it evenly like this. And that's only because what we're going to find is that, like boron and aluminum, gallium, they all like to make 3 bonds. So even though that violates the octet rule, again, we're getting there, right? I'm throwing out words at you. It does like to make compounds with 3, so it does do this hybridization. But I'm only saying it's okay because it reflects reactivity. So both of these would be acceptable in my class on a test for the Lewis dot structure. So does that kind of make sense? And again, all we're getting towards is that our Lewis dot structure should reflect reactivity. So again, going back to beryllium, that's why it's 2 dots on one side, because it's always losing those 2 electrons, right? It's always going to be in that 2+ oxidation state. So then just continuing to march along. So carbon is another funky one. And so carbon, we can just write out the electron configuration. So following our pattern. So again, carbon, 1s2, 2s2. Now we're at 2p2. And of course, write 4 valence electrons. And so carbon is the one exception in group 4. And so again, carbon, we mentioned, is kind of the building block of life. It's also special because it likes to make 4 bonds all the time, right? We said that. And so it's coming up again. And so for carbon's Lewis dot structure, this is appropriate. And so carbon is the only one, so this is, unique. Again, this is reflecting its reactivity in that it likes to make 4 bonds. And I'll write that again. So carbon wants 4 bonds. And so kind of an aside, if we were to look at silicon, because in theory, all these Lewis dot structures should be the same for every family, right? Because they have the same reactivity. Carbon in group 4 is the only exception. So we're going to say all other group 4s would match like this. And so silicon would have 2 together, right, for 2 being in our S. And then for our remaining 2 electrons in our P, we should put them in separate sides to reflect they're actually in separate P orbitals. And so we can kind of break down the electronics argument more. So looking at silicon, I'm going to jump down. So this is, let me go back to this periodic table. So this is 2p. So now if I go 1 under it, this is 3p. I just want to be clear. So then looking at silicon for a second, just so we can appreciate it. So we have 3p and then 3s. And so let's talk about what I drew. And so this is just an energy level diagram representation. And I'm just looking at the valence electrons. So your s orbitals are always lower in energy than your p's. And so we want to, again, fill up our electrons accordingly. So we fill up our s orbital first. So we have 1, 2. Notice I have them with opposite little arrows. So that means spins. And so that just means that each electron has to have a unique spin. So that's why they're like that. So we cannot have this in the same orbital. That's not allowed by quantum mechanics. So that's why it's shown like this. So let's put our half arrow for our electrons. And so now I have 1, 2, but then I need 2 more for my valence. And then these energy levels are called degenerate. And that just means they're all the same. And so if they're the same energy level, that's why we put 1 in each one individually, since that's the most energetically favorable. And why that is is because you have to pay an energy price to pair. So right, once you have those different spins, you have a small repulsive effect. So yes, now that's an energy price to pay. So it is more favorable to put them in their own separate energy levels first before pairing. So that's, again, all we're showing with the Lewis dot structure, and we're translating our electron configurations to, again, our Lewis dot structure. But as we keep working to chapter 3, we'll also be looking at it in this representation. And then before we get kind of too far, let's go back. And so the same little funky arrow thing in the energy levels is also shown on this diagram. So notice, right, they have the 1s on the bottom, so that's showing it's the lowest energy level, then 2s, right, and again, these are all in subsequent energies, or they attempt to show that by the order there. And so again, right, we can click on hydrogen, and oh, there's our one little arrow in the 1s, again signifying our 1 electron. And then if you go over to helium, yes, it does the little half arrows in opposite spins. So that's nice that you can kind of check that. So, right, we can click on silicon, and that's exactly what we just finished writing out, right? So we have our 3p up here with our 2 electrons and their separate orbitals, and then the 3s over there. So again, right, 2 electrons. And then this is just showing, again, your valence electrons is what we drew there. Is that kind of making sense? So 1 no. It's okay if it doesn't make sense. We can go back. Who's confused? What are you confused about, Braden? Which part? So we're just trying to right, we have to kind of define where the electrons are, right? So that's all we're trying to do right now is figure out, well, where do the electrons live, right? And then how does where they live dictate reactivity? Yeah.
Wouldn't it be easier to study, the trends of the table first, like when it increases going that way and when it increases radioactivity going the other way, and then reading the energy levels by going straight across the table?
I mean, different philosophies of how to learn. So I want to revisit the trends. But the thing with the trends is I don't want to just tell you why the trends are. So, right, we could do that. We could say, well, reactivity increases as we go down. But why? So and then, let's answer that, though, because we can answer that with the orbital argument. So that's what we're trying to get at. So I'm kind of going the other way of, starting with the orbitals and building up to the trends. I know you're generally kind of taught the other way, though, right? You just want to memorize all this stuff, but I don't want you to memorize a bunch of chemistry information, right? You have your periodic table and everything is listed there. You just have to decipher it. And so, so again, let's answer the trends question. So what happens to the reactivity as we go down any family? It increases. So why? Because what? I didn't hear you. So the bonds can't be stronger. I'm trying to give you a hint by showing you this little onion ring over and over again. Well, that still doesn't answer our question, right? So that's the whole point of our electron configuration. Well, we've already established they're all in this NS1. Well, what's changing as you go down? What did we mention even just change from hydrogen to lithium?
The reactivity, right?
Yeah, so we said the reactivity increases, but we're trying to answer why still.
Yes.
Shells. So, right, we're adding more shells. So that's it. So that's why, right, so now we can re-relate everything. So we can go back, right? Well, we said, okay, as we go down, and we add our onion rings, okay, it's getting bigger and bigger, right, our shell. But then that also means that NS1 electron, that valence electron, is further and further out, right? As we go down, it corresponds to a new onion ring. And of course, as that electron gets further and further out from the nucleus, then it has a weaker pull, right? So in general, the strength of a charge is, right, Q1 times Q2 over R squared. And so, right, as that distance increases R squared, then of course that force is going to decrease. And so once you have less force on that electron, boom, that's where it flies off, right? So that's again why cesium, the moment you crack that ampule, it's exploded, right? Because it's that one electron is so loose, it just flies off as soon as it literally sees the air. All right.
What
So,
was that formula for again? The Q1?
oh, this is just like strength of charge, roughly. So strength of attraction, sorry. So this is just a general formula, right? So the Q is your charges. And so basically like an aluminum 3+ charge is stronger than like a sodium 1+ charge is what we're saying. So like the more opposite, the more attractive. But again, then you're fighting that radius. So yeah, that's all we're saying.
Why does it go like 1s2, 2s2, and then P? Or sorry, I'm reading this wrong. Yeah, 1s2, 2s2, and then like why does it go from a 1, 2, 2, and not 1, 2, 1, 2?
So that's
Sorry, that's hard to word.
that's where we're building, right? So what we're also saying, so the 1s can only has an s orbital in it. And so that is the only type of orbital that exists in the first energy level, right? Going back to our kind of Bohr model. Then on the second energy level, the s and the p orbital can both exist, but that's it. And then once you get to the third energy level, that's when we finally start invoking the d's. And then fourth one is where the f orbitals start, which is where you get the 36. So is that kind of making more sense to people? And so what I'm also just trying to show you right now by going across is we're just trying to understand the electron configuration and how it fills up, because it does get funky in some portions. So are we okay with electron configurations like up to, like can we do fluorine? Are people comfortable with that? Are we lost?
I know that I have to go back through and read, maybe I'm speaking just for myself, but I know that I have to start, I feel like I have to get a grasp on the orbital, and I know that you just went over that, but I know that I'll have to go back and read and listen to the lecture to really have like a more firm grasp of the structure and how it's being put down. That's just a response.
I took a chemistry class that went over this a year or two ago, and I think at first for me it was a little confusing, but then once you just start doing examples of it, it gets really easy and simple, honestly. So that's just from my experience. I think once you start practicing actually doing them, it gets easier.
So if we're still lost, I guess I'm trying to understand like where we're lost at, because I just don't want to keep marching through, because it's basically what we kind of need to do, but I also don't want to lose people. So I guess like, yeah, I still don't understand what's fuzzy.
So like for example, is number 17 chlorine?
Yeah.
Okay, so like would that be 1s2, 2s2, 2p6, 3s2, 3p5?
Yeah, sorry, 2s2, yeah, 2p6, 3s2, 3p5, yeah. So you just kind of keep filling in order.
I did it last year, so I just
Yeah, but let's slow down, because I think you're ahead of other people that are like still maybe lost on the beginning. So do we understand like how to get electron configuration and what we're trying to do? So some people say no, right? So what we're trying to do is basically, again, put our electrons into where they should exist, right? So this is all the possible orbitals that exist. There's more even theoretically, but then we have to, again, put them in appropriately. And so that's all we're doing with the order, and that's all we're saying, right? So that's all we're trying to attempt to establish by going through this, right? And so that's why I have you kind of write, we start with our 1s orbital, and then these are some things that we just have to kind of accept, right? Like we have to accept that the s is a sphere. That's just gathered, again, from quantum mechanics and computational chemistry, right? We just have to appreciate the pretty picture. And so then, right, we start with our s orbital, and then like we said, okay, now once we can invoke the p orbitals, again, we don't need to understand, right, mathematically how they got there. We just need to understand that there are 3 of them, right, and they look like dumbbells. So kind of that. And then again, right, there's 6 electrons total in the p, and so we're all just trying to build up to reactivity. So let's try fluorine's electron configuration. So take a moment to try to write it on your own. You don't have to. I just asked for the electron configuration, but you could, start thinking about how to translate it. That would be like a good skill and where we want to go though. All right, who wants to give the electron configuration? Sarah, you want to go for it?
Is it 1s2, 2s2, 2p5?
So that looks good. Is that what everybody else got? And again, right, double check, 2 plus 2 plus 5 is 9.
Can you just go through that specific one and just tell me what each part means? Because that's what I need.
Yeah, so then, right, start from the beginning. So that's always the key with these electron configurations, right, is you start at the top. And so that's why you're going to have all these funny scribblings on it, right? So you start with the 1s, so that's why I have 1s there. And then we have to fill up that orbital first, right? So that's what we're saying. So we've just gone through an order, and so you're going to go in order till we hit fluorine. So, okay, so we fill up 1s2, and again, right, the s is 2 wide, so that reminds us, okay, well, only 2 can fit. Then we keep going, so now we maybe need to write a big 2s here. Okay, 2s, 2 again, because again, right, only 2 can fit in the s, and it's 2 wide. Now write your 2p here, and now we have p1, 2, 3, 4, 5. Yeah, and then it should match. And so kind of other things to maybe help you think about it is, so now this is our NP5, right? So all these are going to have the ending, and obviously, right, they're going to have NS2 and P5 there to correspond to, again, there are 7 valence electrons, 5 of those in our p orbital. Did everyone follow with the fluorine at least? Especially Braden, did that kind of make sense back there? Jeremy? Yeah, I mean, it's all just like repeating too, right? Because you should be following along from what I'm telling you, right? I'm like feeding you everything you need to know. And look back at this P table, right? We just went in this same order. We filled up the 1s first, then we did the 2s, and then I know it's hard to tell, but you can just tell, right, the 2p is the next highest. So then, yes, we started filling that one up. And so last thought to kind of chew on, because you kind of mentioned it, and again, we just want to think about all the different ways we can represent this information. So again, pull out, okay, well this tells me I have 7 valence electrons, right? We could write our Lewis dot structure. And again, I want to write it appropriately. So fluorine, I'm going to start with 2 on one side, and then you kind of go around with, you've probably heard it called like the candy rule. So then you just fill up the rest of the 5. So 1, 2, 3, 4, 5, right? So everybody gets an electron until we're forced to pair. So there's our Lewis dot structure. And again, we can start to get more information. Well, oh, look at that, right? It just has 1 lone electron, and so that looks funny. And so that's showing us, right, that it wants to make a bond here. This is starting to hint at why fluorine is diatomic now, right? Not stable by itself. Let's think about other ways to translate that. So you mentioned, you know, should we put this in the orbitals? We should at least think about it. So again, 2p, the p is on top, s is on bottom. 1s orbital, 3 p's, and then fill it up the same way. So we have 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. So same thing, right? And then I filled it up in that order to again show which order the electrons are going to be filling in there.
Wait, sorry, real fast. Are those electrons or valence electrons?
Valence electrons. So I didn't show, right? So I could have just added the 1s, and then it would be all the electrons. But, right, so you want to be able to identify that. Okay, my outermost ones are my valence electrons. These are the core. All right, so there's probably a good place to end, but we're going to keep doing this, right? So we're not done with electron configuration. We haven't gone through some of the funky patterns. So we're going to keep doing this on Monday, but we're also going to keep emphasizing, right, the Lewis dot structures. And then at the end, then we'll tie back to those trends, right, and say, okay, well now these trends make sense because we can explain them using our orbitals. All right, just let me know if you have questions. I'm happy to do office hours after as well. Otherwise, enjoy your weekend, and I will see you on Monday.